Right then. So now in this video, we're gonna do a continuation on reaction quotient. Okay, we're gonna talk about the reaction quotient and what's the importance of the reaction quotient. The reaction quotient, it actually helps us to measure the relative amounts of, say, products and reactants present during a reaction at a particular point in time. Okay, that's what the reaction quotient actually helps us to do of this chemical reaction. Okay, so now the very same reaction quotient, how do we calculate it? We denote reaction quotient as Q. Okay, so we can also use QC. I love it doing it like this. The QC, okay, or you can just write it like this. You can say it's your QC, it's a reaction quotient. Then when you calculate the reaction quotient, you're gonna use the concentrations of your substances. But you need to understand that the quotient, the reaction quotient and the Kc values are not the same thing unless or otherwise. They can be the same under certain condition, but we will talk about that condition, okay? Which is this condition. So now we know that when we want to determine the Kc, we're still going to do the very same thing of the very same reaction. So we're going to say the concentration of the products, in this case, which is C to the power of C, multiplied by the concentration of D to the power of D, divide by the concentration of A to the power of A, multiplied by the concentration of B to the power of B. This is the same expression, but this, it is not the same constant. Let me explain that. How does this actually works? So now, when you want to determine your Kc, you use concentrations at equilibrium. But when you want to calculate your Qc, you use your concentration at any time before equilibrium. Okay, so now this is what is happening. If they say to you concentration of C at equilibrium is 5 molar concentration, that means you can't use 5 over here. You're supposed to use something that is greater or less than 5, because we don't want to use concentration at equilibrium to calculate QC. So if you use concentration at equilibrium to calculate QC and you use concentrations at equilibrium to calculate KC, you're gonna fall under this principle that says if QC and KC are equal, what does that mean? Both forward and the reverse reactions are at equilibrium. It's simply that. Okay, but there are points whereby I love reading it like this. Okay, I'm going to change this. I'm going to say QC. Remember here, KC is greater than Q. That means Q is less than KC, which is the equilibrium constant. Same applies over here. I love reading it from Q because we are calculating Q over here. You can express it in this way. It is still fine. And therefore, when Kc it is less than Q, that means QC will be greater than Kc. All right, I just wanted to read it like this. So now, this is what I want you to know. When Q that we have just calculated over here is greater than the equilibrium constant, what does that mean? It means we have more reactants. So if we have more reactants, equilibrium will shift all the times, will shift to the right. Okay, we're going to explain this, don't worry. Everything will make sense. And then when QC is greater than KC, that means we have more products. So if we have more products, that means equilibrium position will shift to the left. Now, this is what is happening. A lot of learners, they struggle to understand this. They struggle to some sort of memorize this. I have a better plan that will help us to always remember these things. Now, I'm going to open up a timeline over here, okay? Say we have a timeline over here. Even if it's not a straight line, but it's fine. Now, if you have a reaction like this, on the left-hand side, you have your products, and on your right-hand side, you have your, on your left-hand side, you have your reactants. On your product side, you have, on the right-hand side, you have your products. So on this side of the equation, that means I have my reactants, okay? And on this side of the timeline, that means I have my products. Let me write it, products and the reactants. So it won't be, let me fix my pen. It won't be challenging for you to remember on this side you have the reactants, on this side you have the products, because we know that even based on the chemical reaction, right? Number two, we're gonna place our Kc at the middle, Kc, equilibrium constant. Why do I place my Kc at the middle? Because like this is a balance, this is equilibrium, supposed to be at the middle of the reactants and the products. I'm just gonna say that. Now remember, the value of Q can be less than Kc, or the value of Q can be greater than Kc. If this is a timeline, remember that the numbers that are moving towards the products are greater, the numbers that are moving towards the reactants are lesser than Kc. So that means, let me change my pen. So that means the QC that I'm gonna get on this side of the equation is supposed to be greater than Kc, which is 2. If here it's 10, that means here it's more than 10, it could be 12. So that means QC, it is greater than Kc on this side of the timeline. Same applies to here. If I have QC over here, let me change my colored pen actually. If I have my QC over here, I have my QC over here. So that means this QC over here, it is most definitely less than Kc. If it's 10, that means it's supposed to be, it's a timeline. Something which is less than 10, maybe 5. So here Qc is less than Kc. Now, let us talk about everything that we discussed over here to make sense out of this timeline, okay? Just reconstruct this timeline if you forget. Now, when Qc, it is greater than Kc, what does that mean? That means we have more products because this is on the side of the products. That means we have more products or product formed, which is what I have just said over here. When QC is greater than KC, we have more products formed. You can see on your timeline that QC is on the side of the products because it is greater than KC. But when QC it is less than KC, it is on the side of the reactants. That means on this side, we're going to have more reactants formed. Remember, the equation, it is reversible, so you can form the products and the reactants back and forth. So that means QC is on the side of the reactants. Okay. We know that when QC is less than KC, we are talking about more reactants on our chemical equation. Again, now we can see that when QC is greater than KC, we have more products, but we want to reach the equilibrium. So this reaction, what is going to happen with it? The reaction, it will some sort of counteracting the higher side by favoring the what? By favoring the left-hand side of the equation. So when the QC is greater than KC, we have more products. But because QC is on this side of the timeline, it is greater than KC, the equilibrium position of the reaction will shift towards KC, meaning will shift to the left. You see, we can see that this is towards KC, which is to the left. Okay? And then when QC is less than KC, meaning we have more reactants, but the reaction will try to shift to the KC, which is directed to the right. So that means it's going to be right. Our chemical equilibrium will shift to the right, which is towards the KC. So everything that you see over here is everything that I've just explained over here using the timeline, because I know some people, they tend to forget. When KC is less than or greater than, what's happening to the reactants? Where is the reaction going, equilibrium? Where is it, the equilibrium going to shift? So you can use this timeline to remember that all the times. Okay. So now let's have a look at the example of this. So now they say to us a 50 liters reaction vessel contains 1 mole of nitrogen gas and 3 moles of hydrogen gas and 0.5 moles of ammonia. Will more ammonia be formed, or will ammonia dissociate when the reaction mixture approaches equilibrium at this temperature, which is 400 degrees Celsius? So in order for us to answer this question, we're going to use two things. We're going to need the Kc and the reaction quotient. We're going to need these two things. Using these two parameters, we're going to have to determine whether the QC is equals to the Kc, or QC is greater than Kc, or QC it is less than Kc. And from there, we will be able to conclude whether we are talking about more formation of ammonia or dissociation of ammonia in this reaction mixture as this reaction mixture approaches equilibrium. You are given the number of moles of nitrogen gas, number of moles of hydrogen gas, and number of moles of ammonia as this reaction mixture approaches equilibrium, not at equilibrium. If this approaches equilibrium, we can only calculate QC, not Kc. We can calculate Kc at equilibrium. This is any time. So that means this number of moles are at any time. Okay? So now this is what is happening. Everything is simpler. You don't have to draw up that longer table, but you can draw it up if you want to. But in this case, you're not gonna need it. Simply because to calculate concentration, we don't have to do that longer table. We need number of moles and volume. We have number of moles of all species, and then we have the volume, which is 50 liters. So clearly we don't need that. So we're going to calculate concentration of N2 not at equilibrium as this approaches equilibrium, so that we can get QC. So concentration of N2 in this case is going to be given by how much? Now, concentration of N2 is going to be number of moles divided by volume. In this case, number of moles of N2, that's 1 mole divided by 50 liters. And therefore, how much do we get on our calculator? So we're going to say 1 over 50. And then we get 0.02 molar. Now, let us determine the concentration of H2. Determine the concentration of H2, N over V. So N of H2 is 3 moles, and then volume is the same, which is 50. Therefore, we're going to say 3 divided by 50. We get 0.06 molar. Therefore, we need to determine the concentration of NH3. We're going to use number of moles divided by volume, and then the number of moles is 0.5 divided by 50, and therefore how much do we get? By 50, we get 0.01 molar concentration. Now let us determine QC. We're going to say QC, we start with the expression first. We use the, now this is the chemical reaction. We are giving KC, okay? This is the chemical equation. So concentration of the reactants, which is NH3 to the power of 2. It is balanced, right? You need to check that first, don't forget. Divided by the concentration of the reactants, which is N2 as it is. And then multiply by concentration of hydrogen gas. This is 2 to the power of 3. Now let us perform calculations by substituting first. So what's the concentration for NH3? 0.01 to the power of 2 divided by the concentration of N2, in this case 0.02, and therefore for H2 it's 0.01 to the power of 2. Now our QC in this case is going to be equal to how much? I'm going to say 0.01 to the power of 2 divided by 0.02, 0.01 to the power of 2. So here's 3. Let's not make that mistake. It's 3 there. Let me fix it on my calculator. It's 3 there. And then we get 5,000. So now what do you see? Now the question was, are we going to have more products? Or dissociation meaning it's the reverse reaction, or dissociation when of the NH3, are we going to have more formation of NH3 or dissociation of NH3 to nitrogen and hydrogen gas? That's the question. So to answer that question, we managed to get KC. You can roughly do this. Remember the KC in this case, we calculated QC. The KC in this case, it's 0.5, very, very small. So just do your timeline aside, right? KC is in the middle and KC is less, right? But QC is greater. Obviously, it's going to be on the product side. QC is greater. Remember, when QC, it is greater than KC. That means we have more products, right? But we know that the equilibrium will shift to the left, but we don't need to answer that. The question was strictly this one. Therefore, you're going to say more NH3 will be formed. More NH3 will be formed since QC is greater than KC. That's how we apply what we have just learned on the previous slide.